Alrighty, our last Chapter 7 lesson is on power. And as you see here, power is the rate at which energy is being transferred. So we have energy per time, which is joules per second, which is what? What? No, not what? Watt. James Watts. So a watt, 1 joule per second equals 1 watt. So if you have a 60 watt light bulb, you have a 60 joule per second device. So we, of course, as we will see constantly throughout the rest of the year, we have non-calculus and calculus versions of our equation. So first we'll do the non-calculus version of power, and that is always used when the force is constant. So we don't need calculus since the instantaneous force will equal the average force. It's a constant force. There's no change in the force. So power is energy per time, which is work per time. It's the average power. It's also the instantaneous power during the usage because, as we said, the instantaneous force is the average, but it's listed as average, and we have work is F dot delta X. If the force is constant, then we can just lump the delta T with the delta X, and that is V average. So we have F dot V. Again, that would be the average or the instantaneous if the force is constant. The work kinetic energy theorem never goes away. So we could also be on the lookout for, do they give us the change in the kinetic energy in a problem? So that would be the work done divided by the amount of time it took the kinetic energy to change as well. Well, what does the calculus version of power look like? The calculus version of power has to be used if the force is not constant. If the force is not constant, then our timed rate of change of work becomes dw dt, right? The derivative of work with respect to time, and since the force is not constant, the work will not be constant, right? F dot delta x becomes integral f dx. So what we're looking at here is the work is now going to be a function of a position. So for the instantaneous force, the force would be constant for the whole time, but if we let our time interval become small enough, then the instantaneous force remains fixed for that instant, and then the dx dt becomes v. So the dx dt becomes v if we take a small enough time interval where we're going to say the force is not changing over that instant in time. So these are the equations we have to use. If it's a calculus problem, there's only two versions of it. There's the graphical version and the equation version. So if you are literally given work as a function of time, you will be taking the derivative with respect to time to get an equation for the joules, right? All of this would be the joules per second of energy being used, and remember that is a watt. If you were given how the energy transfer was occurring as a function of time, then you would be looking at slopes of secants for the average power. Whoops, let me make that blue. You would be looking at the slopes of the secants for the average power, and of course the instantaneous power is the slope of the tangent. And you should always be on the lookout for zero slope, right? If you have zero slope at that instant in time, there's no time rate of change of energy. It doesn't mean there's no energy. It's just not changing as a function of time. So we'll have a couple of homework questions to look at with power. The main focus for this unit is obviously understanding energy, but since power is a term that is associated with energy usage, especially for electrical equipment, it is good to know how power is introduced into energy.